Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSS sheet. In this we were doing tree topic and the pattern was DFS pattern. Today we'll see the next question, which is balanced binary tree, which is a definition of a binary tree basically. So let's read the problem statement. It says we'll be given a binary tree and you have to check if it is balanced or not. Balanced means height balanced. Means the left maximum height and the right maximum height difference should not be greater than 1. If it is greater than 1, it is not a balanced binary tree. So let's see the constraint. The constraint says minimum number of nodes will be 0 and the maximum number of nodes will be 5000. So we know there are two approaches, BFS and DFS, breadth first search. In breadth first search, we do not need to write the base case if the minimum number of nodes are greater than 0. But as it says the minimum number of node is 0, means for sure we need to write the base case. But in depth first search, whether the minimum number of nodes will be 0 or not, we have to write the base case. Why? Because you have to come out of that recursive function again and again. So there should be some stopping condition for that recursive function, and that is nothing but the base case. So let's see how can we approach this using BFS first, and then we'll see DFS, which is depth first search, later. So here is what you have. Suppose you are standing at a node of the binary tree. So if I'm standing at this node, what I am expecting? Definitely I'm expecting the left maximum height and the right maximum height, and then I'll decide whether their difference, if they are greater than 1, then it means it is not a balanced tree, and if it is equal to 1 or 0, it means it is a balanced tree. Correct? So I can say one thing, if I am standing at node, I will give another, like I'll call another function and I'll give the root dot left and ask it to tell me how many, like what is height, which is basically how many heights are there, levels are there. Correct? Similarly, from root dot right, how many levels are there, because level is nothing but height. So can I say, using the BFS code, I'll call the two functions, which is nothing but for level or a traversal, and the number of levels is nothing but the maximum number of height, and we'll say the difference, we'll check it later. Correct? So first of all, for any BFS code, the very first thing is to make a queue and insert the node. And now until our queue has any element, means until it is not empty, we'll pop the node from the queue. The node is equal to queue dot poll. Once we have node, I want left height and right height. So definitely I'll call for left side and I'll call for right side. I'll make a function, let's say height, where I'll do BF level or traversal, correct? And I'll send root dot left and I will send root dot right, correct? Now once I have, I'll write the check, okay, if my absolute difference between left and right greater than 1, then for sure return false then and there. It means it is not a balanced binary tree. But for 1, you will call the functions, you will get 1 height from the left side and 2 height from the right side. Difference is not greater than 1, means it is a balanced binary node. Now our task is to go towards left side and go towards right side and check for other nodes, which are their children's, left and right. So it needs to go inside the queue. So what I will do, I'll check before inserting in the queue, if root dot left exists, then only in queue offer root dot left. Similarly, if root dot right exists, then only in queue offer root dot right. Very simple. Now after coming outside this whole while loop, if we have not got false return statement, then I can say it is a balanced tree, means return true. Correct? So what will happen? So first 1 will go because 1 is the node. Now we'll pop 1 and we will check their left and right child number of heights. Now then we will insert 2 and 3 as a root child. Again we'll pop 2. For 2 also we'll call and we'll get 2, like 0, 0 as a maximum height. The difference is not greater than 1. Again you will insert their children, but the children are also not there. So next time we'll pop 3. Now we'll check for 3 left and right height, 1, 1, difference is 0, it is still a balanced binary tree. Now it's time for their children to go. So we'll insert 4 and 5. Again for 4 also we'll check 0, 0 height, balanced, 5, 0, 0 height, balanced, means now after popping all, queue will become empty, will come outside the while loop and we can return true then and there. So type So talking about the time complexity, we have iterated for every nodes here, every nodes. And for every nodes, we have called again the level or traversal for n by 2 nodes and n by 2 nodes, correct? Which is nothing but n by 2 plus n by 2, which is n. So for every node, we are again taking O of n time complexity to check the heights, which is actually making it O of n square. So if n was 5000, n square will become 25 into 10 power 6. Although it will get submitted, but it will be very slow. And if it was somehow goes beyond 10 power 8, for sure there will be the chance of getting TLE. How I said this? Because we have discussed about time and space complexity in our full video. I'll attach the link somewhere here. So this code will be slow. Time complexity is n square. Space complexity will be O of n because you are saving all the nodes here in the queue. But for to calculate the height also, there also you are creating an extra queue to store the nodes, which will make it O of 2n total space complexity. So let's write the code for this in the editor. Here is the code what we have discussed. First we'll check the base case because the number of nodes was 0. Now we'll create the queue, we'll insert the root until it becomes empty. We'll pop the node. For every node I'll call that function height for left side and right side. Whatever height it will return, I'll check if the difference is greater than 1, return false then and there, or else both of their children, if they are not null, insert this in the queue and at the end return true. Now in the height function, what you are doing, this is nothing but level or traversal only, but this here you are running the for loop or while loop. So how many number of time you are running the for loop or while loop, this is nothing but the number of levels, and after coming outside you are just doing height plus plus, which is level plus plus, and at the end you are returning. So this is further taking O of n time complexity for every n nodes. That is why the time complexity is n square. So if you will run the code and when you will submit this, definitely this will be slower code, okay, but it is still acceptable. So what is the optimized code for this? That is via DFS approach. So let's see what is a DFS approach. DFS says कि when you are standing on root node, you decide to go either left or right side. So you will go towards left side, and anyhow for any node you cannot decide what is the it is balanced or not until you have the left height and the right height. Means for sure you should go towards the depth, correct? So I'll go towards left side at 2. Again for 2 also I cannot decide, so I'll go towards left side, which is null. So if my root is null, what I should return? Should I simply return? If I'll simply return, how can I check the left height and the right height? Can I say if root is null, return 0? Because for 2 I can say कि left height is 0, right height is 0, and the difference is also 0, means it is balanced node. So in the DFS call where we will call root, we have to check कि if our root is null, return 0, which is integer, correct? Now once I have, I'll go towards left side and right side, correct? So I will go towards left side, and as the return statement is integer, so we have to store the calls also. Means integer left is equal to DFS root dot left. Very good. Now integer right is equal to DFS root dot right. That's it. So what I'll do, from 1 I'll go towards 2, from 2 I'll go towards null. Now I'll go back, return 0. Now 2 is right, again null, return 0. So can I say for 2 I have left and right. So I can do one thing, कि if my absolute difference between left and right is greater than 1, then return false? No. Listen it, we cannot return false. Why? Because the return statement was 0 and you are saving it in integer. So you cannot return a boolean, you have to return integer only. But 0, 1, 2, 3, they are showing the height. So you cannot send the positive number for sure. So can I say return -1? Because negative indicates that it is false, correct? That is why I decided -1, because I cannot take positive numbers for sure. You can return -2, -1, whatever. And you have to check if it is if you're returning -1. Check if your function has returned -1, then return false, like that, okay? So here too we do not have, for 1 you went on 2, for 2 you got, no, it is not, it is a balanced tree, okay? Now, what does 2 expected to send 1? 1 is waiting for left side height, right? But 2's left and right has given 0, 0. So what should 2 return? Think again. Think for 3. 3 has got 1, 1 from left and right. But 3 is expected to return either of these, which is maximum, correct? So is it like 3 is expected to return 1 or it is expected to return 2? Yes. So can I say you have to return maximum of math.maximum of left or right and plus 1. So what 2 will say? 2 has maximum 0, 0. So 2 will return 1 to 1. So can I say 2 will return 1? Now similarly, we'll go towards this. Correct? So talking about the stack calls, in the stack call, first function 1 will go, then function 2 will go. Now for function 2, null null, which has returned, okay. Now function 2 also has returned what? Left side 1. Now it is waiting for right side. So from function 1, you will go for right side, which is function 3. Now for function 3, we will go for function 4. Now from function 4, you called for null, which has returned 0, 0. So for this, it has returned, can I say 1? Yes. So function 4 will return 1. Function 5 will return 1. Correct? And as of now, the maximum, like the difference between, absolute difference between left and right is also not greater than 0. Now what 3 will do? 3 is left and right has been returned, which is 1 and 1. Sorry. Okay. So the maximum is 1 and plus 1. So 3 will return 2 what? 1. Correct? Yes. So 3 will get returned from the stack call and 3 will return 2 as the maximum height from the right side. Done? Yes. And now we'll check the absolute difference between left and right, which is 1 and 2. Absolute difference is 1. It is not greater than 1. So hence will not return minus 1. So what will return? Max of left and right, which is 2 and 1, which is 2, plus 1, which is 3. So from wherever we have called this function, like this DFS function with the root, if it is not equal to minus 1, we can say it is a balanced tree, means return true if it is not minus 1. Okay. So for the very first example, what is the time complexity? We have iterated for each and every nodes. So time complexity is O of n. Talking about the space complexity, we inserted 1 first, then we inserted 2, then we popped 2 and inserted 3, then we inserted 4, then we popped 4 and inserted 5. So can I say from every level you have 1 node? So can I say number of, like the space complexity is nothing but log n instead of O of n, but this is for the balanced binary tree, not for the skewed binary tree. Skewed means this is all you have. The number of nodes will be like this. Means from any one side you have multiple nodes. So as it is a balanced binary tree check, so there might be some tree which is not balanced. So you will end up adding all the nodes in the stack, correct? So the space complexity will go for O of n. Time complexity is also O of n, which is far better approach compared to the previous breadth first search approach, which was taking O of n squared. So for this test case, so it is okay. Now let's see the another test case, which is example number 2. So for example number 2, what will happen? First root. So let's make a stack. First root means function 1 will go. Now function 2. 2 does not has its left child. So 2 will go towards right side, which is function 3. Now 3 also does not have left child, so it will go towards right side, so function 4. Now from function 4 we'll go for function 5. Can I say that? Now function 5 will return 1. So function 5 will return 1. 4's left will return 0. The absolute difference is 1. It is balanced binary tree, so will not return minus 1. Now what will return? Maximum. 1 and 0. What is maximum? 1 plus 1. So 3's right will return 2. 3's left has returned 0. What is the difference between this? 2. Is it greater than 1? Yes. Listen it very carefully. So we will return minus 1. So 3 will return minus 1 instead of 2. So listen. 2's right has returned minus 1. 2's left has returned 0 because it was not there. So 2's left has returned 0. Okay. Like I am showing you how this much code is not enough. 2's left has returned 0. 2's right has returned minus 1 because 2's right was not a balanced tree. So if you will further check, you will get 0 and minus 1. Absolute difference between 0 and minus 1 is 1. So it will say no, it is a balanced tree. So it will return maximum of 0 and 1, like minus 1, which is maximum is 0 plus 1. So it will get from 2's left, it will get 1. Is it correct? No, it is not correct. It will go towards right side, check, it is also balanced tree. So all over it will say it is true. It is a balanced tree, but it is not. Where it was not balanced here only, right side. So when you returned minus 1, so from 2's left it was 0, from 2's right it was minus 1. You went on absolute check, it passed it. It means before that only you have to say na, ki if your left is minus 1, why are you checking this? Return minus 1. Can I say? Means if 2's right was not perfect, then return minus 1. Minus 1 is nothing but false for us, because we were not allowed to return boolean, because we were expected to return integer values. Okay, so for us minus 1 is false. So when our right was minus 1, why are you going to check the absolute check? Let's return minus 1 then and there. So 2 will also return minus 1 to its parent, and as 1's left is minus 1, why are you going to check for right side? Return minus 1 then and there. It means when we have written this left, so we have to check if left is equal to minus 1, return minus 1. Don't go for further checks. Similarly, if right is equal to minus 1, don't check for absolute. Return minus 1 then and there, and that's it. What will happen now? We will, we have got the absolute difference 2, so we have returned minus 1 from 2's right? So after checking 2's right, now it will say, hey, did I receive minus 1 from right side? Yes. So don't go for absolute check, because you just saw absolute check has returned 0 minus 1 difference 1. It was correct, but don't go for it. Return minus 1 to its parent, because 2's right has said it is not balanced tree. Now as 1's left is saying it is not balanced tree, why are you going towards right side? Check if left minus 1, yes, return minus 1. So you will return minus 1 to the main function, which is this. It will say it is equal to minus 1, means it is like this not equal to condition makes it false. It means the return statement will return false, correct? So this is the actual code. Time complexity O of n, space complexity O of n. Why O of n, not logarithmic of n? Because it is not, it does not mention that every t will be balanced. What if it is q tree? Then it will be O of n. So let's write the code in the editor. So here is the code what we have discussed. First we will make the height, which is DFS function for us, and we'll check if it returns minus 1, then true or false accordingly. First we'll check the base case inside it. If root is null, return 0. Why base case is important? Because of two reasons. Constraint says a minimum number of nodes can be 0 first, and second, as we are doing the recursively, we are going towards depth, so for sure one time the root will become null. Now after that we'll go towards left side and right side. If root return minus 1, return minus 1 then and there. Why it was important? I just showed you in the example key before checking the absolute, because sometimes even if left side is 0 and right side is minus 1, the absolute will say yes, it is valid, because the absolute difference is not greater than 1, correct? So it is very important to check if left returns minus 1, return minus 1 then and there, vice versa for right also, and then the absolute difference, and what we are supposed to return to our parent is nothing but the maximum of left height or right height, and plus including the node 1 to it, correct? So this was your DFS code. The time and space complexity is linear and O of n. Okay, that is why it is faster also. So this is the Java code. Here is your C++ code with a similar approach, and here is your Python code with a similar approach. So if you understood this, congrats. We can go in the sheet and mark the next question from the DFS pattern, which is balanced binary tree. So do hit the like button if you understood this, and I hope you are making your notes along with understanding the problem and submitting the solution. If you have any doubt, you can reach out to me through social media. I'll attach the link of the social media and the sheet link in the description. That's it guys. If you're really liking the videos, do hit the subscribe button if not yet subscribed, and you can even recommend the channel to your friends, because we are learning pattern wise DSA, not only for trees but for every topic. So that's it for this video. Let's meet in another video with some more interesting questions, topics and patterns. Till then, keep learning, take care of yourself and your family too.